Okay, let's get started. You are working your way through now your second weekly milestone where you're gradually digesting your 4 bite-sized chunks for your final project. Couple of reminders and clarifications about the final project. You might find as you start to tackle your second weekly milestone that maybe what you had in mind wasn't quite what you're interested in doing now. If you make changes to your final project, perfectly fine. Just make sure that in this or any of the following weekly milestones, you tell us. My original plan was to do this, and my remaining M3 and M4 was supposed to be this. I now want to do this, so I'm changing my M3 and M4 to this. Just let us know. Pivots are perfectly fine. We're not holding you to what you committed to last Tuesday. Okay, other things to talk about the final project is you're working your way towards an A/B test, and we talked a little bit about the statistics of that last time. Main takeaway, make sure that you do enough runs of your A and enough runs of your B to be able to confidently say at the end of this class, there's no difference between A and B. A is better or B is better. Doesn't matter to us which of those 3 outcomes happen. It's not up to you. It's up to Mother Nature, which of those is true. Have enough data so that you can say something confidently. If you have a couple runs of A and a couple runs of B and say, well, it kind of looks like A is better than B, but I don't have enough data to be sure, that's not great. Okay. Another thing I want to talk about is, I mentioned this in passing last time, which is apples to oranges comparisons. So the best way to visualize all of the data from your final project is using fitness curves, which we've seen many times now. We've got evolutionary time on the horizontal axis and F on the vertical axis. This presupposes that your fitness values in A are the same fitness values as in B. Your fitness function in A is the same as your fitness function in B. So I used the Brainiac project last time as an example. You're making in B the robot's brain a little bit bigger, but you're using the same fitness function, forward travel in 1,000 times steps of the simulation. In the final project documentation, I used up, and away as an example. What happens if you want to evolve high jumping and long jumping? Those have 2 different fitness values, so how do we go about comparing them? Tricky. Ultimately, you want to collapse your A/B testing back to do an apples-to-apples comparison. How do they do on both? Yeah? Okay, there's many different ways to do an apple-to-apples comparison. I'll just show you one today, which is using a trick we've already looked at, which is multi-objective optimization. So if we have one fitness that you're most interested in, so if we go back to the up, and away example, it's how long can the robot keep all 4 feet off the ground? Let's imagine that's F1. That's the thing that you're interested in. You could think, well, maybe the best way for it to keep all 4 feet off the ground is to select for that and to select for overall height of the robot. I always forget whether Y or Z is the height in pi bullet, but it doesn't matter. If we were to evolve against these 2 objectives, what behavior are we selecting for? I don't want to act it out because I'm going to throw my back out, right? Jump as high as possible and keep your feet off the ground for as long as possible. We could imagine that this is A. You might imagine that possibly selecting for or evolving for the long jump is better for ultimately evolving the robot to keep all 4 feet off the ground for as long as possible. So if this is A, this might be your X. This might be your B. So here we're evolving for stay aloft for as long as possible and do the long jump or maximize X. So we can now ask the question, which of those 2 variants ultimately produces a better F1? The thing that you're really interested in is keep all 4 feet off the ground. In this discussion, it might seem odd because if this is what we're interested in, why don't we just evolve for that? Isn't that the best thing to do? Turns out in a lot of cases, that's not the case. I don't know if there's any gardeners here, but you might find that if you garden in such a way that you always select for the plants that have the biggest tomatoes, after a while that doesn't work very well. It's often a good idea to select for plants that produce large tomatoes and something else. I'm not a gardener, so I don't know what else. But often exerting selection pressure directly and only on the one thing that you're interested in causes your evolutionary algorithm or your tomato plants to get stuck on a local optimum, and then they can't get off it. If you select for something else, you're kind of pushing your population in different directions around the fitness landscape, and in some cases, you can make it easier to escape local optimum. Make sense? Questions? Confusion? The secondary thing here, this is the thing that we're kind of using as a scaffold, which we've seen several times in this course. This is often known as the auxiliary fitness function, or in machine learning, the auxiliary loss function. It's kind of a helper thing to help you ultimately get to the thing that you want. Okay, this is one approach to make sure that ultimately, even if you're interested in slightly different things like high jumping and long jumping, ultimately you're doing an apples to apples comparison. At the end, you're going to show us how well long jumping and high jumping did against the main thing that you're interested in, keeping all 4 feet off the ground. If A is high jumping and B is long jumping, in this hypothetical example, selecting for high jumping actually ended up producing robots that kept all 4 feet off the ground longer than if you selected for long jumping. Okay, any other questions about apples to apples or apples to oranges before we get back to lecture? All good? Okay. All right. I realize I went a little bit too quickly at the end last time. We're in good shape. We've got plenty of time in the remainder of the course for our remaining 4 lectures. So I want to jump back to evolving rigid bodies and brains for a moment and go back over co-evolution, because this is actually a common technique in evolutionary algorithms and machine learning. I think I went a little quickly through this. So just to remember, we're looking at this example, this groundbreaking experiment from over 20 years ago by Carl Sims. We have our virtual creatures. Carl Sims did a number of experiments, one of them in which there were the 2 creatures that were competing over a common block, which means that the fitness of any one individual is not fixed. The fitness of an individual can change based on what the other individuals in the population or populations are doing. Okay, so how do we do this? Let's start by assuming what we're most familiar with, which is a single population of robots. We take one robot, represented by the circle in the top here, and we run n-1 simulations if n is the number of robots in the population. We compete this robot one at a time against all the other n-1 robots. Then we go on to robot number 2 in the population, compete it against the other n-1 robots in the population, and so on. The fan on your laptop is probably on quite a lot these days because, as you now know, evolutionary algorithms plus physics engines is very computationally expensive. You're expending n simulations per generation, where n is the number of robots in the population. How many simulations are we running in total if we have n robots in the population in this setup, known as all versus all? We're competing each robot against all other n-1 robots in the population. How many simulations are we running as a function of n?
N choose 2, so n times n-1 over 2.
N times n-1, right? So we've got to go around this circle n times, and every time we do, at each stop in this circle, we do n-1. which is n times n minus 1, y divided by 2.
Because you'll have, if you have A compete against B, and then the next time you have B compete against A, you're doubling the competition.
Exactly. We know what the outcome is if we're going to compete A versus B. We don't need to run the simulation of B compared to A. It's symmetric. We're going to get the same outcome. Okay, so n over n minus 1, hugely computationally expensive. Carl had the benefit of the CM5 machine at the time. You don't. So he was interested in how do we do this more efficiently. At the other end of the spectrum, we can do this. How many simulations do we need to run in this case?
4.
Sorry?
4.
4, as you can see here, and as a function of n?
N over 2.
N over 2, right? It's actually more computationally efficient than what you're running on your laptop these days. Obviously problematic. What's the problem? Why don't we just do this?
Say you have two sets compete and 2 of them come out on top, but what if the ones that lost what one that came out on top would have been beat by the one that lost in the other set of competing?
Exactly, right? So you may know from competitive sports, if you've got an idea that you're probably going to be the silver medalist, you know the other competitors in the population, you know you're about second best, and in the round you get paired up randomly with the other individual who's expected to get the gold medal. Right? You're in trouble. You're going to lose, and you're going to look no better in terms of your fitness value from the person who actually is the worst if we had done this. So this is great. It's computationally efficient, but it gives us at the end of any one generation, it gives us a very poor estimate of the overall fitness of each individual in the population. So pros and cons to both approaches. So again, taking a page out of professional sports here, we can do round robin. We can pair everybody up randomly and take the winner from each local competition. So we do n over 2 simulations. Take all the winners, put them together, do n over 4 simulations, repeat, repeat, repeat until we get to the semifinals where we do 2 simulations with the 4 finalists, and then finally the final round, 1 simulation of the 2 best from those competitions. Slightly less computationally efficient than B. What do we gain from doing the tournament? We're going to do a few more simulations, a little bit more than n over 2.
Get a singular most fit result from it instead of a bunch of most fit results.
Well, everybody's still going to have a fitness value. At the end of all of these, we have a single floating point number for everybody. How reliable are those fitness values?
They're more reliable than random. Like at least you have levels of.
So there's some individuals that are going to go through several simulations, right? So we're getting a better estimate for them. We're not getting a good estimate for everybody, though. Who are we getting a poor fitness estimate for?
The ones that lose early.
The ones that lose early, right? So again, if the silver medalist is very unlucky and gets paired up with the gold medalist and is immediately knocked out of the round, that looks like they have a very poor fitness. But unbeknownst to us, if we had done this, they would have actually got the silver medal. So we're balancing, or Carl was balancing, the amount of computational effort against estimating fitness, which is really important because at the end of each generation, we're going to use fitness to determine who lives and who dies.
For the competitions here, I thought that the evolutionary algorithms just choose the best one overall, and it's kind of all versus all, but there's not a bunch of that. What are the actual competitions for? Or is this for the block snagging?
This is the block snagging. The fitness value is how close you are to the block and how far your competitor is away from the block. at the end of that simulation. You get back a single fitness value. Now, for example, in the all versus all and the tournament, there are some individuals in the population at one generation that are participating in multiple competitions. So we're getting back fitness values for that individual from multiple simulations against different partners. And I don't know if Carl mentioned it in the paper, but he's probably taking the average of all those fitness values. We're getting a better and better fitness estimate about how good somebody is at grabbing the block and keeping their competitor away from the block. That's what I mean by fitness estimate. Okay. So Carl came up with a fourth option, which he called all versus best, which is it's not shown here in this picture, but in the very first generation, when you've got a population of random robots, you do all versus all. So it's computationally expensive, takes a little while to do this first generation, but you have a very good fitness estimate for everybody in the population, at least at that time. You then take the best, the individual that had the highest fitness, and in the next generation, everybody else competes against the best individual from the previous population, otherwise known as king or queen of the hill, right? There's someone who's on top who has the highest fitness value, and everybody else is attempting to push that robot off the hill, the top of the local optima, or wherever it happens to sit in the fitness landscape. Okay. That means that we have a pretty poor estimate of all the other incumbents, all the ones down here that are trying to knock the king or queen off the hill. But it doesn't matter. If any one of these individuals happens to outcompete the best in the population, we're actually getting a pretty good fitness estimate for that competitor, because they're competing against someone who's survived many simulations and possibly many generations. So if any new individual that arrives in the population through mutation or crossover manages to unseat the king or queen of the hill, as you can guess, that individual becomes the king or queen of the hill in the next generation. So again, we're finally balancing fitness estimation against computational efficiency. How many individuals do we need to evaluate in each generation when we do all versus best as a function of n? N minus 1. Okay. All right, there we go. All right, you notice that for each, or at least for 3 of the 4, Carl ran an additional set of experiments where now, instead of a single population, he's got 2 populations. I introduced this idea briefly last time. It's worth going into. So in this case, when we run an evolutionary algorithm like this, as before, when we start the evolutionary algorithm, we create a population of random robots. And then we just create a second separate population of random robots. And now we still have to figure out how to estimate the fitness of our 2n robots now. We can compete every individual in population 1 against every individual in population 2, which is n. And then we evaluate every individual in the other population against every individual in the first population. You can see from this huge mass of lines that all versus all in this co-evolutionary setup, also very computationally expensive. We can do random with 2 populations, and we can also do all versus best between these 2 populations or species. Why is tournament missing in the co-evolutionary setup? How would you do tournament with 2 populations?
It's just essentially a 1v1 in the last step, the last generation or competition is going to be the best of one with the best of the other, so it's only +1.
Possibly. Can we still do the tournament though?
You could do a tournament, but the the separate species?
So we could do it. I don't know why Carl didn't do it. There's ways to do it. I think, yeah, you'd start by randomly picking one individual from population 1, one individual from population 2, and you're doing all the original competitions, and then you do the semifinalists from both against both populations. For whatever reason, he didn't do it. What he found worked the best. And when you saw the video of all the robots competing against the common resource, it was coming from algorithm variant G. We were talking about A/B testing just a few minutes ago. This is A through G testing. We have the champion in each population. It survived a lot of competitions. It's possibly survived a lot of generations. And every individual in population 2 is trying to unseat the best from population 1 and vice versa. Okay, co-evolutionary algorithms, quite common. If this is something you want to try in your final project, go for it. If you get a little bit confused, come on by office hours and we can talk about how to do it. Okay, I also went very quickly last time through co-evolutionary dynamics. So what happens when we have populations that are competing against one another? When we talked about fitness landscapes way back when we were talking about evolutionary algorithms, we assumed the fitness landscape is fixed. It's a landscape. It looks something like this. Imagine we have just one parameter theta that's being evolved, and for any value of theta, we can measure the amount of fitness. As we saw when we talked about evolutionary algorithms, they can get stuck. Well, that's not stuck. That's global optimum. They can get stuck on local optimum. So evolutionary algorithms are always dealing with populations for the simple reason that if you have a whole bunch of searchers searching on a hilly landscape, you increase the probability that someone won't get stuck on a local optimum. Yeah? Okay. When you have a co-evolutionary situation, we have one population that is experiencing this fitness landscape. I'm a competitor, and for various values of theta, this is how well I do against the other guys in the other population. Yeah? If I have a value of theta of this, this is how well I do on average against the other guys in the other population. The other population, let's see if I can draw this with one color, has a different fitness landscape. In this other population, if I have a theta of this, I do really poorly against these guys. In this other population, if I have a theta value of this, I compete very well against the other guys in the population, until the other guys in the other population start to evolve counter strategies for this strategy. Once that starts to happen, what happens in this part of the fitness landscape for these guys? Let's imagine this strategy is knock the other guy very far away from the block. And the other guys start to evolve that strategy of standing up and rolling on top of your arm. What happens here for this population? It's not that the fitness function decreases, the fitness landscape decreases. This is no longer a good strategy because there's been some evolutionary change in the other population. So if you think about it, you can imagine a whole bunch of points, the individuals in population 1 sitting at various points on this fitness C. It's a wavy surface now that's changing its shape over evolutionary time. And we have individuals in population 2 sitting on their own fitness C that is also changing. Everybody see that? You've updated your mental model of fitness landscapes and co-evolutionary fitness landscapes. In this situation, in co-evolving populations of robots and co-evolving organisms, weird things start to happen, like, for example, this situation down here, which I mentioned briefly last time. What's happening here? We've got population 1 and population 2. What happened?
Population 1 like hit a point where it was just so much better that the other population just wasn't able to get out of their local optima and beat them.
Absolutely, right? So population 1 evolved a strategy of some huge, massive, heavy arm that falls on top of any individual in population 2, and any individual in population 2 is literally crushed. Can't move, can't do anything. Mutated offspring, crossed offspring, they all similarly are crushed underneath the heavy arm of individuals from population 1. You get co-evolutionary collapse. The C for population 2 now looks like this. No matter what value of theta you have, you get a fitness of 0. You never get close to the block because you're squirming underneath this heavy arm. Unfortunately, this happens in nature as well. One of the canonical examples of a co-evolutionary system in nature is in the northern reaches of Canada. You have lynx, big cats, which I'll call L here, and Arctic hares with an H, the rabbits with the big floppy ears. These guys love to eat these guys. So you've got the population of lynx over a few years or a few decades. The population of lynx goes up. There's more and more predators which love to eat hares. Hares at the same time are going up, but as there's more and more lynx, the number of hares start to decrease because they're getting eaten by all the lynx, which means the number of hares start to go down, and as there's fewer and fewer hares, there's less and less for the lynx to eat, and so their population starts to go down as well. I realize I've misdrawn this. Let me start again. Let's start with the prey species, hares. So hares start to increase, and as they increase, that's good news for the lynx. So the lynx start to go up, but as the number of lynx start to go up, they're eating more and more hares, which causes the population of hares to decrease. The lynx go up for a while. Now they start to starve and die off. They drop down. The number of lynx is decreasing, which is good news for the hares. There's less predation. They start to go up. And if this is H, you get the population of lynx following behind the population of hares, and you get this oscillation, which you can kind of see happening in a few of these plots here. If the number of lynx increases too quickly, they eat all the hares, and if the population of hares gets too low, and then there's a disease that kicks in or something goes wrong in this very small population of hares, it's over. No more hares, which eventually is not good news for the lynx as well. Yeah? Okay. Again, for those of you that are interested in this aspect of evolutionary biology, it's an idea you can play around with in your final project. Okay. Questions, comments about that? All right. So, finally finished our discussion about evolving bodies and brains for rigid robots. Let's move on to soft robotics. One of the trends that's been going on in robotics as a whole over the last 10 or 15 years is thanks to materials science. We're getting a larger and larger range of interesting materials that we can build our robots from, and we no longer need to build robots from steel and plastic and ceramics, which is maybe good news because some of these robots are going to be very close to humans. There was that Disney Pixar movie a few years ago, Big Hero, that big blimpy-like soft robot. There's obvious good reasons for wanting to be soft. One of them is that you're safe, but that's not the only one. Our good old friend, the octopus, as always, demonstrates, in this case, another reason why you might want to be small. Imagine we want to develop robots that can navigate a disaster site. After a natural disaster, we want a robot to be able to crawl through the rubble and locate human survivors. In that kind of cluttered environment, there's a good reason for wanting to be soft. You'll notice that the octopus has a hard time right at the end here. Why? It's not the brain. Brains are soft. It's one rigid part to octopi. The beak. You got to be able to eat, right? Okay. Despite that, you can navigate very narrow apertures. So back to sort of pure engineering of robotics. There are many environments in which it's probably easier for soft robots to navigate than rigid robots. Professor Cheney, who teaches the evolutionary algorithms class, which is kind of the sister course to this course, back when he was a graduate student, got his hands on one of the very first soft body simulators, which you can see here. And together with our colleague Hod Lipson, we came up with this idea, which is basically, let's demonstrate evolving soft bodies and brains for robots to do exactly what the octopus did. You'll notice that Nick published this paper in 2015. I mentioned he got his hands on, at that time, the very first soft-bodied simulator, which had been reported in the literature 1 year before, in 2014. So we're going to take a few minutes now and talk about what does a soft-body simulator actually do, and then we'll come back to Nick's experiments and see how he used it to evolve soft bodies and brains. Okay. As you can see in the drawing here, in the soft-bodied simulator, all of the parts are going to be represented as flexible cubes. And if we approximate the body of our robot with a large enough collection of small enough cubes, we can increasingly approximate very complex three-dimensional shapes. The simulation you're going to see here is known as VoxCAD or VoxCraft, which is obviously a nod to Minecraft. Everything here is going to be built from cubes. Okay, so let's talk about the graphics of the physics engine first, and then we'll go down and talk about the physics. Remember that, or at least you can tell from this picture, every cube in VoxCAD, I'll use VoxCAD for now, every cube in VoxCAD has 6 neighbors. So you can't see the central cube here, but every cube is attached to 6, unless that cube happens to be on the edge of the structure, and then it's got less than 6 neighbors. Well, we're going to draw all of the cubes touching one another. And here's a simulation not of a robot, but this is just demonstrating the fact that VoxCAD can simulate soft materials. Imagine we made a bar of rubber, like you see here, and we stuck one end of the bar against the wall and just let go of this bar of rubber. In reality, and in the simulation, you get something that looks kind of like this. You'll notice, obviously, it's bending, it's being pulled down by gravity. You can see that it's made from a soft material that eventually resists the pull of gravity and bounces back up again. Rubber and a lot of other soft materials are cousins of springs. They have stiffnesses and they have damping coefficients. A lot of soft materials, when you hit them, if they're attached to something, they'll deflect away from the force and then come back again. Yeah? Okay. So you're seeing something that acts more or less like you would expect a bar of rubber to. What do you think the rainbow picture is showing? And what do you think the red-blue picture is showing? Any mechanical or civil engineers in this class? I don't remember.
Assume the red-blue is probably the type of material at each voxel.
The red-blue is the type of material. So I misled you a little bit. I said we're simulating a bar of rubber. Not quite. We're actually simulating a structure that has 2 different materials in it. There's some rubber, and then there's something else. In the red-blue plot, which is which? Is rubber the red or rubber the blue? is red. How do you know?
Well, because the red is the only part that's flexing.
Flexing or deforming, right? So if you look carefully, you'll notice that the red cubes themselves are changing their shape, but the blue ones are not. So this is an inclusion of some rigid material. Hard plastic, steel, doesn't really matter for our purposes. But if you look very carefully in the red-blue plot, you can see that the blue cubes are not changing their shape. They're displacing, they're being pulled down, but they're holding their shape. Anybody want to take a guess at the rainbow plots?
Is it the stress?
It's the stress, right? How much force or strain are these cubes feeling? As you can guess, in this lecture, we're going to take a bit of a digression into material science, materials engineering. Yeah? Okay, so we haven't talked too much about the physics yet. This is what things look like as a result of the physics. Remember in PyBullet also separates the physics from the drawing. Physics always happens, but you can choose to visualize or not the underlying physics. So in VoxCAD, we're also separating the graphics from the physics. All right, let's have a look at the physics. I want you to imagine the picture in the upper left here. Imagine that all of these 7 cubes stay where they are, but they shrink. They get a little bit smaller, which gives us this picture over here. You can't see it in the graphics, but every pair of neighboring cubes has a beam connecting them together. These beams are the things that actually have the material properties, plastic, rubber, or steel. The cubes are just drawn, they're the eye candy. They're just drawn to show you what this structure looks like. What's actually happening in the physics is it's a truss. It's just a whole lattice of beams connected together. So far, so good? Okay. All right. Let's think about these beams for a moment. In VoxCAD, every beam has 6 numbers attached to it, 2 sets of 3 numbers, K and K sub phi. K is the usual letter that's chosen for stiffness when we're talking about springs or materials or whatever we're talking about. How much that material resists being pushed or pulled upon, that's K. So a big wound coil of steel is a spring that has a very high value of K. A slinky is a spring that has a very, very low value of K, stiffness. Okay, so what's the difference between K and K sub phi? K is a set of 3 numbers that describes how that beam resists being pushed and pulled across the 3 spatial dimensions. So if this is my beam, how much does the beam resist being pushed in the x-axis, the y-axis, and how much does the beam resist being pulled and compressed along its own axis? A triplet of k's that has a very high first value and a very low second and third value means it's very stiff. It's going to resist this force, but it's not going to resist forces that are pulling and pushing in this direction, and it's not going to resist extension and compression. When I mention a big, thick steel spring and a slinky, the intuition there is all the K's are high for the steel spring, and all the K's are very low for the slinky. Here we're getting fancy, and we can set how much it resists pushing and pulling in different directions. So far, so good? Anybody want to guess about what K sub phi is now?
Like torsional stiffness?
Torsional meaning related to torque, which is rotational force. How much that beam is going to resist rotational forces, and I never get my yaw, pitch, and roll right, but K sub phi is going to dictate how much that beam resists this. I can never do this. Yeah, you know what I mean. You can twist it in 3 different directions. So all 6 of those numbers taken together is going to dictate how stiff or soft this beam is along those 6 different ways of pushing or pulling or twisting the beam. So far, so good? As you can see from this picture, every individual beam can have its own set of stiffnesses. You can make a composite of a whole bunch of beams stuck together that are stiff or soft in different ways. Okay, so we just talked about stiffness, which is how much the material resists forces, F sub A. We'll just ignore the A for our purposes today. So F is a number, is a vector with 6 numbers in it. How much horizontal force is being applied to the object, how much vertical force is being applied, how much force in this direction, how much torsional force or rotational force in this direction, and the other 2, which I can never remember. Yeah? Okay, so at every place where the beams come together, VoxCAD, like pi bullet, sums up all the forces that are acting there. So for example, if there is a force that's pushing inward on this cube, inward on this cube, inward on this cube, inward, 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 there are 6 forces, compressive forces, arriving at this node down here. 6 forces. VoxCAD will just sum up all of those forces. There is also a mass sitting here. Sorry, I misspoke when I said there's nothing where the beams meet. There is something there. It's something that has a certain mass. The geometry of this thing doesn't really matter for our purposes. Okay, so VoxCAD knows all the forces that are acting on this cube, including, for example, the downward force of gravity, whatever else is going on. It sums up all the forces, it knows the masses, and it uses F equals ma. It rearranges that equation so that it can use F and A to compute, it uses F and M to compute A, acceleration. F, remember, is a vector of 6 numbers. We won't worry about how mass is encoded, but we get back 6 numbers for A. How much this cube is now going to accelerate at the next time step, horizontally, vertically, and forward and back, and how much it's going to accelerate in terms of yaw, pitch, and roll. The rate at which it's going to increase or decrease rotation, like we did before. So in this cartoon example here, this little red dot is meant to represent where the cube was at the previous time step. The VoxCAD summed up all the forces, knew the masses, computed the new acceleration, applied that acceleration to the current position and orientation of the cube at the previous time step, uses that acceleration to update the new position and the new orientation of the object sitting at the nexus of these 6 beams. Everybody see that? Okay, that's it. That's how VoxCAD works. You put a whole bunch of these together and you paint stiffnesses onto these beams. Hint, hint. I'm giving you a hint about how we're going to evolve robots in a moment. And you get materials that more or less look right. What do you think? Do you think the sim to real gap here is wider between a soft bodied simulator and a real piece of soft material, or sim to real between rigid materials, between pi bullet and the evil starfish, for example? Absolutely. So we can now simulate a wider range of materials. We talk about soft-bodied simulators, but it actually includes also rigid materials. We could just make all the Ks very high, and we could simulate rigid robots in VoxCAD. The cost, of course, of this expansion of the materials that we can simulate is we've also widened the sim-to-real gap, which we'll see in a few minutes. Okay. All right. One of my students who actually took this class a few years ago created a GUI front end for it, and this became known as VoxCraft because you can go in and craft your own soft body material. So what you're going to see in a moment is a user manually building a body, not for a robot yet, but for a three-dimensional structure. So the interface, you can go download it and play it around with it yourself. It has sort of a CAD front end. And what you can do in the panels over on the right is choose cubes with different material properties. Sita just chose flexible. Flexible are red cubes. So these are cubes that are being connected together with low stiffness beams. It's a little hard to see here, but you can also click on stiff cubes, which are going to be shown in blue. Here comes some blue cubes. Blue cubes are connected to one another with stiff beams. You can see that in the CAD simulator, you build this up layer by layer. Let me just pause for a moment. It's a little difficult to see over here, but obviously we've got a little bit of a stiff, soft sandwich going on over here. How do we simulate, or how do you think VoxCAD simulates a stiff cube attached to a soft cube? So here's our stiff cube. It's being attached to a soft cube. How do we do it?
Does it either take the maximum stiffness or the average of the stiffnesses?
Exactly. So there's a beam sitting inside. This cube tends to want to have high K values. This cube wants to have low K. We could take the average or the maximum of one. If you have a steel cube and a rubber cube and you glue them together, how does that thing operate? We don't take the maximum because that would be the soft cube becoming more like the steel cube or vice versa. So what they do in VoxCAD is cut this beam in half and assign small K values to this half beam and high K values to this beam, and they weld this piece together. Now that I talk about it, I imagine it works out to the same as averaging out the Ks. I don't think it really matters. Okay. Okay, they're going to, in the interface here, you can set some other physical details of these materials, which we haven't talked about, not really important for our purposes. Okay, now we're going to see this creature being simulated. They're building up the suspense here. It's breathing. Why is it breathing? There's an additional detail that's being built into the structure that we haven't talked about yet.
Are these the central pattern generators?
Central pattern generators. So what we just talked through actually are, again, the objects and joints. There's no strict joints here. It's the beams connecting these pieces together, but we've got a physical structure, and now, surprise, surprise, we're going to start to layer on motors, sensors, neurons, and synapses like we did in the Carl Sims experiment last time. So the first thing we're adding on here are motors. So we've got some motors that are controlling this robot, and we're connecting a central pattern generator, something that just spits out a sinusoidal pattern, and it's sending these values, high force, low force, or high force, high desired force, low desired force, to the motors. Where are the motors in this system, do you think? Where are the motors sitting, and what are they pulling and pushing on?
In the connections between the objects.
in the connections between it. I just mentioned we cut this beam in half. Imagine we put a motor right in the center, and that motor can push the two half beams apart or compress or pull them together. The motors could also do the other 5 forces that we talked about. In this case, the motors only apply forces pushing those 2 beams apart and trying to pull them together. If we attach a central pattern generator to that motor, it's going to rhythmically extend and compress every half beam, which it's doing in this simulation, and this is the result you get. The robot doesn't, now we can start to talk about a robot. This robot doesn't go anywhere. Why not? Unless somebody pulls on it.
Doesn't have any motors?
It has motors. The motors are actually changing the robot. You can see it deforming, but it doesn't displace. It doesn't move anywhere.
It's got stiff layer, and the stiff layer is not letting it bend to like move like a snake or anything.
Possibly, right? So the blue middle layer is possibly too stiff. It's kind of stiffen up, and the red ones can't move enough to get the whole structure moving. Possibly. Other ideas?
The motors also aren't firing strong enough to really get it off the ground to move.
Possibly, right? So one of the things about being soft, going back to our lecture about locomotion, is you drag a lot of stuff, right? It's very hard to get most of your mass off the ground. The red stuff on the bottom is soft. Think of this as like silicone or rubber. It's dragging. It's like our poor lizards that have to exert a lot of energy to displace because they're dragging. So the motors probably aren't strong enough. The stiff inner core is resisting the overall structure really deforming and getting able to like take a step or shuffle or move. 1/3 thing that is also obstructing motion here. You're all becoming experts in biomechanics. There's something else about this that's making it hard for this thing to actually move.
If you put this thing up on its side, it seems like it would move more.
Oh, possibly. So we go back to our little triangle robot that we started this course with. Let me play the gate for you again. There's no oscillation in the gate. There's definitely an oscillation in the overall structure. Every motor is getting what signal? The same signal, right? So everything is, I don't know how many beams there are inside this robot, but every beam is getting exactly this oscillation where everything is moving together. If I do that, I'm not going anywhere either, right? We need multiple signals that have phase offset. Once things start to oscillate, but oscillate at different phase offsets, then you get motion. So I don't have a video of this, but you can imagine that if you leave everything the same in this robot and the only change you make is to set phase offsets in the signal arriving at all the motors inside this robot, it still may not go anywhere, but it's more likely to start to move a little bit in one direction or the other. Again, going back to the triangle robot you started this course with, if the triangle robot all moved in phase, it didn't really go anywhere either. If all the motors stayed in phase in that triangle robot. Okay, everyone have a good grounding in objects, links, and motors. So far, so good. Is this open or closed loop control? This is open loop control, right? Closed loop control, just as a reminder, sense, think, act. And when you act, that causes changes in your sensor values, which causes changes in how you translate sensation into action. Closed loop here, right? What we're looking at the moment is open loop control. There are no sensors yet. The thinking, so to speak, is just the central pattern generators doing their thing and dictating actions. Okay. Okay, I mentioned the sim to real gap. As you can imagine, it's ferocious. So 7 years ago, some of my colleagues at Yale, we teamed up to try and cross the gap. And you can probably guess from looking at this picture, we didn't do so well. It's tricky. Okay, so how did we do this? What you saw in the graphics is that each individual cube gets a little bit bigger and a little bit smaller in simulation. Looks good, but how exactly would we do this in reality? My Yale colleagues came up with the following idea, which is to make the soft cubes from VoxCraft, make them soft in reality. Make them out of silicone. This is a very soft rubber, which you can see here. And these cubes are hollow. There's nothing inside. You'll notice these little tubes coming off here. So some of these tubes connect with some of these voxels, three-dimensional pixels. And if we send compressed air using a syringe into these cubes, they get a little bit bigger. And if we pull the syringe, if we pull air out of the cube, out of the hollow cube or the hollow voxel, it gets smaller. It actually collapses in on itself and assumes very complex 3D geometries, which is very problematic. This is tricky to simulate in reality. But if you squint, default size, default volume, bigger, smaller. Okay. 7 years ago, this is as far as we got. We made the quadruped, and you can see that there's one tube here that's supplying air into and pulling it out of the robot, so it's almost literally breathing here. Air in, air out, and surprise, surprise, this robot isn't going anywhere yet. Again, for the reasons we just talked about. There's one signal going into all the cubes, all of the cubes. Not quite all the cubes. You'll notice that the legs don't breathe. So some of these voxels, some of these cubes, we punched a small hole in their adjoining wall and sealed it up. So there's an air channel that can go from one cube to the other. Some of the cubes do not have holes punched in their walls. They're self-contained. No air goes in or no air goes out. But of course, the movement of some of these voxels pulls the other independent voxels along with it. Okay. If you're feeling ambitious, you got nothing to do this summer, you can go to the VoxCraft website that I showed you before, and there's a bill of materials that costs about $200 on Amazon. You can buy those materials, which you see on the right over here, and you can actually try making your own physical voxel bot. One of the things you'll buy is what's called dragon skin. That's what's in the yellow bottle there. Dragon skin is liquid silicone. When you heat it up, it'll set and become solid. So you're going to see some of this liquid dragon skin being poured into this mold. And we're going to start by creating the 5 sides of the soft voxels. This fancy machine that you see on the right here, you don't have to buy this part. This is just sort of for fun. You're going to see in a moment it's going to rotate, and it's going to help coat the inner surface of this mold with this liquid dragon skin. We've now cooked some of this dragon skin. We're going to cook some of this dragon skin for a few minutes, and it becomes solid. You're going to add another layer just to thicken these walls. Not a lot of complex engineering here. This is almost, cooking level. Not that difficult. Okay, let me skip ahead a little bit. Okay, so now the dragon skin has set and it's become solid rubber, solid silicone. We're going to gradually cut it out. And now we've got our soft hollow cubes with 5 of the 6 faces. Remember that I mentioned when we built the robot, some of the neighboring cubes had a little air passageway between them. So here's my then grad student Sam gluing 4 of these pieces together. And he's now going to punch holes through some of the neighboring cubes. So when we supply pressurized air in or pull pressurized air out, it's going to flow through a subset of these cubes. Pour a little bit more dragon skin, which is liquid at room temperature. Get a uniform layer of this material. And then seal up these 4 voxels. We want to make sure that everything's airtight because we're going to try and control this with pressurized air in a moment. The dragon skin has now set. If you leave it for long enough, it will also solidify at room temperature. Okay. Now we've got a little roll of very small tubing. We're going to thread it inside one of the voxels and seal it up. So again, it's airtight, no air escapes. Sam has now made 2 of these. We're going to connect them together to make a 3-dimensional structure, and using just a normal syringe, we can now supply air to a subset of the voxels. The little Y that you see here, this is ensuring that air goes equally into both chambers. Where do we punch holes? Where do we place voxels? You don't know, I don't know. You can guess where we're going with all this. Okay. All right, let's turn to Nick's experiment. So we have our simulation. In theory, we can make real versions of anything we simulate. Whether or not we'll cross the gap, that remains to be seen. How do we go about evolving bodies and brains for these kinds of creatures? Here's a particular soft robot taken from early in an evolutionary algorithm, and here's the great-great-great-grandchild of that robot. So just to visualize evolutionary progress here, what a surprise. We're going to evolve robots to move to the right as quickly as possible, as we always do. Okay. You'll notice that there are non-random distributions of red, green, and you can't quite see it, but there's a little bit of light blue in the back here. Another hint. What evolutionary algorithm do you think Nick used to construct these bodies or evolve these bodies? Neat evolves neural networks, so we're close. We're painting different colors in 3-dimensional space here, where colors represent the stiffness of the beams. We're actually painting stiffnesses onto beams, and we're going to represent those stiffnesses with different colors. Hyperneat, exactly. So just to remind you, what does Hyperneat do? It uses neat to evolve neural networks, but it evolves specific types of neural networks called compositional pattern-producing networks. Here's one CPPN here, and this CPPN has been architected to paint colors into 3-dimensional space. Remember that a CPPN takes as input a bunch of positions in 3-dimensional space. So we've got our empty cube cage here. We're going to walk through this cube and visit a bunch of points in this cube. We're going to uniformly distribute points, and we're going to visit one point at a time. For every point, we're going to take its x, y, and z coordinates. Forget D for a moment. We'll come back to D. We're going to take the x, y, and z coordinates of that point, push it through a CPPN, and at the end, in this CPPN, we're going to fix 2 output neurons. The value arriving at the first output neuron, we're going to scale that, we're going to binarize it to a binary value. So the value that arrives at the first output neuron is either 0 or 1, and it dictates whether or not to place a voxel at that position or not. In this cartoon example here, where this is the phenotype and this is the genotype, most of the points do not receive a voxel. Most of the time, when we feed in 3D coordinates, we get back a 0 at the presence question mark output neuron. The second output neuron is going to paint a material onto a voxel if we place a voxel at that position. So far, so good? Okay. You'll notice that in this experiment, there's 3 different colors here, green, blue, and red. There's actually a 4th color, which is dark blue. You just don't see it in this cartoon. So the value arriving at this second motor neuron in this experiment, we're going to discretize that value to an integer 1, 2, 3, or 4. Green, red, light blue, or dark blue. Okay. Let's watch evolution in action. It's a great summary. This is a great summary video of this paper, in my opinion, because we're going to actually see evolutionary progress. Let me pause for a moment. Okay, here's the 4 colors. Red and green are going to represent muscle. That, if we watch for a moment here, you'll notice that they're just spontaneously getting bigger and smaller. Red, we're going to feed every red voxel, we're going to give it this central pattern generator pattern. So when I restart this video, you're going to see all the red voxels get bigger together and smaller together. All of the green voxels are going to have motors attached to them as well, or have motors inside them, and they're going to receive a different phase offset central pattern generator value. So all the green voxels are going to get bigger together and smaller together. But whenever red voxels get big, the green ones are getting smaller. And whenever the red ones are getting smaller, the green ones are going to be getting bigger. Why did Nick set up his muscles in his robots in this way?
We have muscles that flex and extend.
So we have agonist and antagonist muscle groups, agonist and antagonist muscle groups. And as we just talked about a few minutes ago, if all the voxels are getting bigger together and smaller together, no matter what the shape of this robot is, it ain't going anywhere, right? We need phase offset to start to get displacement. Okay. Light blue is going to represent the soft robot equivalent of fat or skin tissue. It's stuff that can be pushed and pulled easily by neighboring voxels. The K values inside the light blue voxels, high or low? Low. They're soft, right? So when we say that the CPPN is painting blue, it's painting blue, and blue means make all the K values inside that voxel low, and don't add a motor here. They're passive soft support. Okay. Then we're going to have bone down here as well, the 4th and final material property. So if the CPPN paints dark blue onto a voxel, it's stiff. It's hard like bone, so it's going to paint high K values onto the 6 beams inside that cube, and it's also not going to place any motors onto those 6 beams. It's rigid but passive. So we've got basically quote-unquote muscle, quote-unquote fat or skin, or tendons if you like, and quote-unquote bone, passive rigid material. Okay, we got 5 minutes left, so we'll finish with this video. Let's see what HyperNeat does with this setup. You're going to see in the first part of this video, you're going to see, I guess you're going to see some final evolved solutions first. So there's a creature made up of some red, light blue, and dark blue. All 4 materials. You can get something that kind of looks like walking. When the media reported on this paper, they referred to them as Jello bots for obvious reasons. Okay, so those are some of the things that evolution produced. Let's see what evolution looks like. This is a random CPPN. This is a random CPPN in generation 0. This random CPPN is painting, as always, a non-random solution, which is mostly fat. Generation 1, we're already getting rightward displacement. Generation 3, 4, 10, something like that. Generation 40. Generation 120. What's the dominant material or materials so far?
Muscle.
Right? We told evolution, make something that moves as far as possible, and it basically very quickly starts to evolve huge balls of muscle. Perverse instantiation? Kind of. We gave it soft material and rigid material thinking that would be helpful. Maybe it's not. Remember the 4 desiderata of locomotion. What balance is this evolutionary algorithm striking? It's favoring some of those desiderata and ignoring others, or discarding others.
Displacement.
It's favoring displacement and ignoring or not caring about.
Blanking on the name of it, but like how structurally sound it is.
Not quite.
Energy expenditure.
Energy of expenditure, right? There's no penalty for using a lot of energy in this evolutionary algorithm, so what a surprise, it evolves big balls of muscle that have agonist and antagonist muscle groups, right? You need that phase offset. We've actually seen this simulation before. I just didn't talk about it very much. Where did we see it? There was something else that was flailing around like this. The xenobots, right? Several years after this paper, we adopted this simulator and HyperNeat to evolve simulated xenobots, which are made up of frog skin cells, which are soft. Okay, just for fun, let's have a look at some of the things that evolved. Some of them do actually make a bit of use of passive soft material and rigid material. Definitely not the most energetically efficient ways to get from left to right. So the ministry of silly walks when it comes to soft robots becomes much, much larger. Question?
How would you implement like energy expenditure within the loss function or the fitness function?
We started this lecture talking about BOO, bi-objective optimization, maximize displacement, minimize use of energy. Try and push a Pareto front down and to the right.
What would be your like analog to energy expenditure though?
Okay, great question. Yeah, great question. The sim to real gap here is wide. We're still working on crossing it. But I showed you that one way to actuate these things is to have a human holding a syringe and pushing air in and pulling air out with the syringe. So what's the metric for this?
Do you wanna minimize the amount of muscle?
Amount of muscle effort on the point of view of the grad student who's sitting here and pushing and pulling the syringe. Imagine we made one of these things about this big, and I give you a syringe that's this big, and you've got to pull and push. Absolutely, the amount you have to do this and the speed at which you have to do this is a very good approximation for this. Or whatever automated machine is actually going to do the pulling and pushing. Okay, we're out of time for today. We'll continue this lecture next Tuesday. You got a quiz tonight, and you're working on M2. Have a good rest of your week.